Assalamualaikum and a very good day. Today we are going to cover chapter 4.7G on bypass. Bypass and recycle are merely the same. They are the same. Okay. We can say that they are just a mirror image to each other. Bypass is a fraction of a stream. Okay. If you can see, we have a splitter here. Some fraction of the stream X value is sent and diverted around one or more units and combined with the output or sent into a very specific unit. Okay, so recycle and bypass calculations, to solve them, you can solve them in the same manner. So you will have a few points. For example, you can make your splitter as one point of analysis, and the point where they are mixing together is another point of analysis. So you can see that here, this is an example. It is just, as I mentioned, a mirror image of what you have in the recycle stream. So you can have the splitter and a mixing point, splitter and a mixing point, and a splitter and a mixing point. So you can draw and label, and the overall balance and balance around the system you can use to determine the unknown. So you can have this as the boundary 1, boundary 2, boundary 1, boundary 2, boundary 1, boundary 2. Okay, but remember, for splitting, there is only one independent equations. Okay, at splitting point, there is only one independent equations. Okay, because you are just removing a certain portion of the stream only. All right, okay, so what we have here, this figure actually shows a unit operation that operates with bypass. Okay, in this example, we have a feed material here that is consisted of A and B, and A is has 80%. You can have it mass per mass, you can have it mole per mole, and B is also 20%. Okay, so the feed comes from tower 1, which is our storage compartment or storage tank. It goes into tower 2. Some of the feed is actually some fraction of feed, you send it to tower 2. Some fraction is bypassed so that it meets with the product from tower 2 to make sure that it meets the client specification of A to be 90% and B 10%. All right. So for the stream that goes into tower 2, where the separation of A and B occurs, we can see that here the separation occur perfectly, even though this is actually not what happened, okay, in industry. So you have a very perfectly separation between A and B. You can see that you have recover 100% of B as a top product, and A 100% of A as the bottom product. So for all of this, we are able to see that the compositions of each of the components are known. Okay, what are the composition of A and B for X stream? They are just similar to our feed stream because it is just a splitting point. Similar to stream that is actually going into the mixing point, this one here also have similar properties as A and B from our feed stream. So here you can see that again, the product specification by our client is 90% and 10%. So we need to find the amount of X that is splitted, okay, that is sent to tower 2. So to solve for X, what we can do is we can start with our first concept of boundary analysis. So as I shown here, this yellow golden box is the first boundary that we can set up for this system. Okay, you don't need to set it up to cover this tower 1 because there is nothing else happen in tower 1. Right? So we can look into just tower 2 because there are stream going into tower 2, there are stream going out as product and also side. So we have feed that is coming in here and we have product that is going out and we have side that is going up. Okay, the next boundary that we can have where there are changes in terms of the property of the stream is at our splitting point. But remember, at our splitting point, we have only one independent equation. All right, we only have one independent equation. We cannot have two independent equations because they are the same. Okay, it will be the same between x and also the stream that is meeting at the mixing point. Okay, the third point or the third boundary that we can have is at the mixing point. Okay, where you mix your feed stream, portion of the feed stream with the product coming out as the bottom product of T2. Okay, so the third boundary is there. So we have everything set up as the boundary analysis. Now label all your known and unknown. What are your known information? What are your unknown information? So your unknown information will be the amount of feed, the amount of X, the amount of site, and the amount of products. What are your known information? Your known informations are the mole fractions of all of the stream, right? Then you can calculate the DOF. Okay, remember, is it a reactive or is it a non-reactive system? If it is a reactive system, you can use either atomic balance, molecular balance, or extent of reaction. If it is a non-reactive, then you can just identify the number of unknowns, look into the independent molecular species, and any other information that you know. Okay? Rank the DOF, find which one that have DOF equals to 0. Okay, and then if you can start by solving the equations with DOF equals to 0, right? Start up your total material balance. For example, feed is equals to site plus product, and you do the component balance that where you can balance A and B. Okay, and also to assist you in your DOF calculations or DOF analysis, then what kind of other information that you need? Is there any way that you can make sure that the DOF can be 0? Okay, so any information on the stream values, for example, yes, then you can proceed with the calculation and you can put it into your setup equations. If there is no, then you can go with the basis. All right, you can set up a basis equation. So once all of these are set up, you can check, you can recheck to make sure that your DOF are not over specified when you put in the basis, right? Okay, that will conclude our sections for bypass and